When Aisha hits send on a digital message to Rahul, the data leaves her computer and begins its journey across a physical network connection. But that network hardware does not understand words, characters, or distinct files. Down at the physical layer, a cable only carries a continuous, unbroken stream of voltage variations or light pulses. If Aisha sends one message and then a second one immediately after, the network transmits those pulses back to back. There are no natural spaces or physical indicators built into the hardware to separate them. On Rahul's end, his computer's receiving sensor simply accumulates an undifferentiated river of ones and zeros. The system has no inherent way to determine where the first message stops and the second begins. Without a specific mechanism to mark the start and end boundaries of a data payload, the network produces meaningless noise, making digital communication impossible. To fix this, networks use a technique called framing. Before the data leaves the sender, the system wraps the raw message in clear boundary markers. The receiving computer relies entirely on these specific markers. By scanning the incoming stream for the exact byte pattern of a start or end command, it knows exactly when to begin recording a message and when to stop. But this introduces a dangerous edge case. Suppose Aisha types a completely ordinary word, like weekend. That string of text naturally contains the letters E and D in sequence. When Ralph's receiver sees that pattern in the middle of the message, it triggers a false positive. The system prematurely stops listening, corrupts the incomplete message, and drops the rest of the legitimate data into the void. This highlights the rule of data transparency. A framing system is only viable if it can transport any arbitrary user data without confusing the user's text for the network's internal delivery instructions. Engineers solve this ambiguity with software armor known as byte stuffing. The sender scans the message and inserts an escape character directly in front of any sequence matching a boundary marker. The receiver detects this escape character, consumes it, and safely processes the following data, no matter what it looks like. This logic applies recursively to cover secondary edge cases. If Aisha intentionally types the literal escape character as part of her message, the sender simply stuffs a second escape character right in front of it. Other methods exist to measure boundaries, like counting the exact number of characters, or by using invalid physical signal pulses. But these alternatives are prone to cascading error propagation, or are strictly limited by specific hardware constraints. Byte stuffing empowers character-oriented networks to trust the integrity of their boundaries. It actively neutralizes dangerous data patterns before transmission, ensuring the envelope never collapses on the contents. This problem exists beneath the character level, too. Many systems bypass text characters entirely, transmitting only raw, continuous binary bits. In bit-oriented systems, the boundary marker is called a flag. The most common flag is a specific fixed sequence, a 0 followed by exactly 6 consecutive ones, and ending with another 0. The dangerous trap remains exactly the same. Any random file, image, or compressed data packet naturally produces a sequence of 6 ones, accidentally triggering a false flag boundary. To prevent this, the sender uses bit stuffing. The moment it counts 5 consecutive ones, it forces a single 0 into the stream, shifting the message backward. The receiver operates on the exact mirror process. It counts incoming ones. When it sees 5 ones in a row, it automatically deletes the very next bit if it is a 0. By artificially breaking up long sequences, this simple counting rule mathematically guarantees the true flag pattern remains completely unique, preventing digital collisions at the lowest logical level of communication. While byte stuffing operates in distinct 8-bit blocks, bit stuffing works on a continuous single-bit stream. Both achieve the exact same structural goal, but at different granularities. This structural guarantee comes with an engineering cost, variable overhead. Because the amount of stuffed data depends entirely on how many dangerous patterns happen to be in the original message, the final size of the transmitted frame is unpredictable. It is also important to note what framing does not do. It offers zero encryption or data protection itself. The data is structurally intact but completely exposed. Yet framing is mandatory for security to function. It operates at the data link layer, the foundational tier that organizes raw bits into readable units. Without this structure, higher-level security checks like digital signatures or checksums have nothing to verify. Network architecture requires compromises. Engineers willingly accept the processing cost and variable overhead of stuffing because the absolute guarantee of a message's structural integrity is worth the trade. These specific algorithms are built into the literal hardware and protocols that keep modern life connected. Many standard broadband connections rely on the point-to-point protocol, which uses byte stuffing. Meanwhile, high-speed corporate networks and the physical USB cable connecting a keyboard to a computer rely heavily on bit stuffing. When Aisha's message finally arrives at Rahul's computer, the receiver detects the true boundaries and strips away its engineering armor, cleanly removing every stuffed bit. Every text, streaming video, and digital transaction relies on this continuous, invisible cycle. Framing and stuffing run quietly underneath it all, preserving the meaning of human communication across the physical void.